Hey everybody, I want to talk to you about how to do two sample hypothesis tests. And we're going to do a bunch of confidence intervals in here too, just to get some practice. So there's three types of tests that we're going to go over. And I kind of just want to jump straight into them. So let's get going here. So the way you can tell we're doing a two sample hypothesis test is if we have two samples that we're comparing to each other, as opposed to one to a number and another to another number, right? We have two samples that we're comparing to each other, and we are interested in the difference between the means or the proportions, depending on if we're doing numerical or categorical data. So, do men or women make more money on average? Do Republicans or Democrats support this particular bill more? Right, something like that. So where we're comparing two things and we're interested in the difference between them. All right, so there's three types of tests that we're going to do. I know it sounded like there's only two there, but there are three tests that we're going to do. There's a two sample t-test, a two proportion z-test, and a paired t-test, which is really kind of different than the other two. I just realized my picture is in the way there. If we have two samples that are being compared to each other. There is technically a two sample z-test where we use a z distribution, which is to say we know the population standard deviation. It's very unlikely that that ever comes up. In fact, the very first line of section 10.2, which is the chapter in the book where they go over this, is although this situation is unlikely. And I agree with them. So we are skipping that. Yeah, so we'll talk about the kind of tests that we're going to do, but we're going to kick it off with the basic two sample t-test. All right, whoop, too far. All right, so we're going to test to see whether boys or girls spend the same amount of time per day playing sports or not. Oh, and I should say, this is the point in the course where I'm going to lean into the calculator a lot, which reminds me of one thing. Hang on a sec. I'll be right back. All right, I'm back. I had to go make sure my calculator was working, and it was not. So I'm glad I did that. All right, let me get back to what I was saying, which is we're going to do a test the thing I was saying was I'm going to lean into the calculator significantly more than we have in the past. At this point in the course, the formulas you can do, if you watched perhaps my previous video on test statistics and transforming distributions, or the video on confidence intervals, you might notice that the formulas are getting kind of big. They're actually not too big to use by hand yet, but after this point, they will be. Basically, I mean, you can technically do it all by hand, but that's not good. Even the American Statistical Association says we should not teach in that way, and I 100% agree. We have technology, we're going to use technology. So I'm going to be leaning into the test functions in the calculator and using more stuff in the spreadsheets that we've got. So yeah, I'm not going to be right now test statistics or anything like that. We're just going to kind of figure out what we're doing, write some hypotheses, and jam it all in the calculator. That's the plan anyway. So anyway, let's do it. So we're going to test to see whether boys and girls spend the same amount of time per day playing sports. So we observe 18 boys and 20 girls, and we find these things. Boys average 2.1 hours per day playing sports with a standard deviation of 0.86, and the girls average 1.8 hours per day with a standard deviation of 1.13. Now, you might notice, if you're reading carefully, and I hope you are, that these are from our sample, right? So these are from our observations. This is not some sort of general blanket statement about boys and girls. This is the things we saw in our sample. So this is our sample mean, sample standard deviation. So we're going to conduct hypothesis tests and make confidence intervals for the difference. So let's, before we do that, maybe calm down a little bit and read a little more carefully and label everything, right? So that's what I'm going to be doing here. So we observe 38 children. That number is not that relevant. 18 boys and 20 girls. So 18 boys. So this is going to be N sub B. And this is going to be N sub G. The boys average 2.1 hours per day playing sports. So that is pretty clearly X bar B, with a standard deviation of 0.86 hours per day. That is SB. Girls average 1.8 hours per day, so that is X bar G, with a standard deviation of 1.13 hours per day, so that's going to be S sub G. All right, so it's a little hard to read the labels, but we can figure out what they mean. I want to go back and look. Conduct a hypothesis test to determine if boys and girls spend the same amount of time playing sports. One thing you might notice here is I did not specify an alpha. So since I didn't specify one, we are going to default to alpha equals 5%, 0.05. And then make a confidence interval. And again, I didn't specify a confidence level, so our confidence level is going to be 95%. So we're just going to use the defaults here, and I believe I did that on all the problems for my example here, or for my examples. So let's go do it. All right, so 2 sample t. All right, so we want to conduct a hypothesis test. So in conducting a hypothesis test, the very first thing we must do is, well, determine what kind of hypothesis test we're going to do. I'm not going to write that in here, but we'll talk about it. And then we're going to write some hypotheses. So we have 2 different samples here, boys and girls, and we are testing to see whether boys and girls spend the same amount of time per day playing sports with the implied or not, right? Same amount of time per day playing sports or not. So we have 2 samples that we are comparing to each other, and we want to know about the difference in the relevant population means, right? So we've got 2 sample means, and we're going to use that to estimate the difference in the population means, or in the first case, determine whether that difference exists or not. And then in the confidence interval, we'll estimate the difference. So that means that I am interested in whether or not the boys or whether the mean for boys equals the mean for girls. So we can write that in a couple of ways. We can write that as mu sub b equals mu. Oh, I didn't write that these were hypotheses. Pardon me. Let's try that again. All right. So my null hypothesis is mu sub b equals mu sub g. Now we can certainly write this way as well. Mu sub b minus mu sub g equals 0. And you might say, well, why would I want to do that? The first one seems more intuitive, and it does. Writing it in this second way can sometimes make it easier to tell what your alternative hypothesis should be. So for instance, let's write an alternative hypothesis here, and I'm going to write the wrong one first, right? Let's say that now in the problem statement, it said, we want to find out if there's a difference or not. So this should pretty clearly be not equal to. But let's say we wanted to find out if boys spent more time playing sports than girls. Then we might write something like this: mu sub b is greater than mu sub g. And it's not necessarily trivial to tell what, how can I say this? If we were writing out the test statistic, this one would be harder to use. And then something like this, mu sub b minus mu sub g greater than 0, then this one would be easier to use. In general, we're not going to be doing that. So it can be useful to write the alternative hypotheses like this some of the time. I'm not going to. I think I'm just going to stick to the first way pretty much all the time. Maybe there's a situation where I'll go back on that and write it the other way, but I'm not going to worry about it for right now. It also turns out to be surprisingly tricky to determine the direction of the alternative hypothesis if you write it the other way. So I'm just going to stick to this. And then we've got all the material, or excuse me, all the statistics written down on the previous board. I don't know why it's not. Oh, I see. You got all the statistics written down on the previous board. So I think I'm pretty much ready to jam this into the calculator. Let's go calculator this thing up. So calculator, there we go. All right, so we are doing I should mention that what kind of test we're going to do, right? We already figured that out, but let's go look anyway. We got means and standard deviations here, and we want to find the difference between them. So we're doing a 2 sample t-test. I actually maybe should have called, I kind of want to call this a 2 independent samples t-test. We'll talk about this more when we get to paired. They're dependent samples and paired. But this is what your calculator calls it. So this is what I'm opting to call it is 2 sample T. But this is where the samples are independent of each other. The boys and the girls, like one boy is not particularly related to one girl. And we'll talk about that more when we get to paired. So I'm going to go to stat and tests and 2 sample t-test, this guy right here. And of course, it wants data or statistics. I gave you stats. In general, if I give you data, I'll give it to you in a spreadsheet because it's so much easier to handle than it is in a calculator. The typing is easier. I can just give you a file instead of making you type a bunch of stuff, which is usually what I want to do. And so we're going to probably use stats pretty much all the time. Even when I give it to you in spreadsheet form, you might want to find the stats in the spreadsheet and then put those into the calculator to do the analysis. Sheets doesn't have much in the way of like hypothesis testing capabilities that I know of. So 2 sample t-test, that's what we're trying to do here. So I need to decide whether we're going to make boys or girls 1 or 2, and it doesn't matter which decision we make, we just have to choose one. I'm just going to let boys be 1 and girls be 2, since that's the order I presented them in here. So we've got N1 and X bar 1 and S1. I don't know what order to ask for them in, but let's remember what they are. N1 is 18, X bar 1 is 2.1, and S1 is 0.86. So let's go with the calculator. X bar 1 is I already forget. No, it's 2.1. Good. I did remember. SX1 is 0.86 and N1 was 18. And then for the girls, I don't remember what these numbers were because I didn't try to when we were looking at them. Girls, 1.8 hours per day, standard deviation of 1.13. There were 20 of them. Okay. 1.8 hours per day, standard deviation of 1.13 hours. There were 20 of them, and we are doing not equal to. Is that actually what I wrote? That's what I meant to write. I feel like I wrote greater than. Hang on. I did. What a turkey I am. That's not correct. Like I said, I was demonstrating that to show how sometimes you could get sometimes it could be a little bit hard to tell what direction to make the alternative hypothesis, but pretty clearly from the way it was stated, I want to not equal to here. So let's go check that in the calculator. And as I mentioned before, when we were talking about confidence intervals, we're just going to leave pooled on no. That has some minor issues in that you get fewer degrees of freedom. And if the sample sizes are wildly different, it can have an effect on the test, but it's really not worth worrying about as far as I'm concerned. We're just going to leave it on no, rather than trying to explain what pooled standard deviation is and all the calculations behind it and the extra hypothesis test you have to run. Maybe we'll do this a little bit later after we do some F testing. All right, calculate it up. So t-score of 0.926, p-value of 36%. We're not going to be rejecting the null hypothesis here. So even though this seems like a pretty significant difference, right? 2.1 versus 1.8 hours, right? That's 0.3 hours difference, or about 20 minutes difference per day. This is not enough information for us to be convinced that boys and girls play sports a significantly different amount, primarily because of the relatively high standard deviations and relatively low sample sizes. So high standard deviation, low sample size is going to make it quite hard to reject the null hypothesis in general, even when the difference between the means is reasonably large, like this one is. So yeah, no way to reject the null hypothesis here. Let me show you what I would want to see on a test if you did something like this. So I want to see something like 2 sample T. Test x1 bar equals 2.1, s1 equals 0.86, n1 equals 18, x2 bar equals 1.8, s2 equals 1.13, and n2 equals 20, right? And so if you show me that on your test or your homework or whatever, I know what you've done, right? And then you can just kind of say the p-value, right? P-value equals or about equal to 36%. Don't reject the null hypothesis. And then let's make a nice conclusion here. I didn't leave myself enough room for the confidence interval, but that's okay. Our conclusion is this is not enough evidence to suggest that boys and girls play sports a different amount of time per day. All right, let's see if we can cram this all into the little room I've got here. Hello? It didn't take my typing. Okay. There we go. There you go. I think that's all I wanted to say. We should make a confidence interval as well. I'm going to have to do that on a blank new screen because I only gave myself one blank screen to do this all on. I've got portion problems coming up there. Oh, that's going to be wonky in the whiteboard stuff. I'm sorry. It's going to be a little weird, but let's do the let's do the confidence interval. So I'm going to draw this. So it's going to be part B. So my confidence interval is going to look something like this. Well, I'm going to do the same thing. I'm just going to do a 2-sample T confidence interval. Or I think that's what they call it. Or 2-sample T interval is what your calculator calls it. I'm going to go ahead and go to the calculator. So I've got all this stuff written down now. I don't really need to do anything else. Notice that the degrees of freedom they did were that weird calculation that we saw in the test statistics video. Yeah, so let's go to stat and test and 2-sample T interval, which was 0 here. And we've got the same exact stuff, right? 2.1, is this all correct? This is all correct, 95%, that looks great, cool, no. Calculate it up, and there's our interval, negative 0.3576 to 0.95757. So the thing you want to see is what this interval represents. Let me write it down actually. Let's call it 0.358, 0.958. Shoot, 2-sample T interval. Forget the numbers by the time I'm done writing this. Sample T interval, same data. As hypothesis test. And we end up with an interval that look like this, negative 0.358 up to 0.958. Is it 8? I don't remember. I knew I was going to forget the number. 358 to 9. Oh, hey, I did remember it correctly. What do you know? Great. Okay, so that's the interval we get. So I would say something like this. Where's my text? We are 95% confident that, here, let me stretch this out so we get a little more room. The mean difference between the amount of time boys and girls spend playing sports is between negative 0.358 and 0.958 hours per day, with negative hours corresponding to to girls spending more time playing sports and vice versa. Okay. So the thing I want to point out here is that 0 is in this interval. That means that a difference of 0 is what we would consider a reasonable value for the population differences, for the difference between the population means, which is to say that we think that no difference between boys and girls is a reasonable interpretation of this data, which is the same thing as saying that we don't reject the null hypothesis, right? So let's go back quite a few screens here. Right, when we don't reject the null hypothesis, that's the same thing as saying we think it's reasonable to say that the average number of hours per day that boys spend playing sports is equal to the average number of hours per day that girls spend playing sports. Right, that's what not rejecting the null hypothesis means. And so that goes with a confidence interval that contains 0. Right, that's another way of saying the same thing, that 0, no difference, is a reasonable interpretation of our data. So that's the connection between hypothesis tests and confidence intervals. If you do one, you can always do the other, although I will say this. When we do a confidence interval here, we're actually doing what's called a two-sided confidence interval, because when we did when we found our 95%, right, that's all the critical value stuff where we find the middle 95%. We found the middle 95%, right? The extra 5% was chopped into 2 pieces on the outsides. You can do a confidence interval that goes just to the left or just to the right and has infinity on one side of it. And those go with one-sided hypothesis tests. So confidence intervals matching up with hypothesis tests doesn't work exactly right unless your hypothesis test is two-sided, which is to say it has a not equal to alternative hypothesis like ours did here, right? Our alternative hypothesis was not equal to, and so it's going to correspond with the, our result on the hypothesis test will correspond with our result on the confidence interval, which is to say 0 could be in the interval because it's reasonable to think that the difference between boys and girls is 0. So if we're not doing a two-sided hypothesis test, if you want to do want your confidence interval to match up perfectly, I can show you how to do that. I'm not going to worry about it here. I'm not going to do that. Doing that is just distracting from the main thrust of what we're doing. If this is a thing that you get into doing more, or if you're just interested in learning about it, I'll be happy to show you how to do it. But it's not going to be a main thrust of what we're doing. Anyway, let's do another example. All right, I want to do a 2 proportion test this time. So we're still thinking about boys and girls in sports here. And so now we don't want to see, now we're not checking to see whether boys or girls spend more time playing sports. Now we want to see if there's a difference in the proportions who enjoy it. So we want to know whether a higher proportion of boys or girls enjoy playing sports. So we ask 76 boys and 81 girls, all 10 years or less, if they enjoy playing sports. 68 of the boys and 70 of the girls say yes. Okay, we'll do a hypothesis test and make a confidence interval. I'm going to read this a little bit slower and label the numbers. So 76 boys, I need to draw out, have text. 76 boys were how many we asked. So that's going to be the wrong color. That should be pink. Can't do this without pink. That just wouldn't be correct. This is N sub B. 81 girls. That would be N sub G. The 10, not relevant. That's just telling us how old the boys and girls were. 68 of the boys, so that would be X sub B. And 70 of the girls, that's going to be X sub G. And we're going to do a hypothesis test. So we have to figure out, well, number one, what's alpha? I didn't specify, so it's 5%, right? No alpha specified means alpha equals 5%. And then make a confidence interval. We'll do that in a little bit. So I'm going to do a 2 proportion Z hypothesis test. So let's go to a blank space, page. That's not the right thing to hit. I left myself a blank page. Hang on. Right here. There we go. All right, so part A, we need to write some hypotheses. We already know what kind of test we're doing. We're going to do a two proportion Z hypothesis test. Null hypothesis, alternative hypothesis. Our null hypothesis is going to be the proportion of boys that enjoy playing sports is equal to the proportion of girls that enjoy playing sports. Now, did we see if we had a rooting interest here? If the same proportion of boys and girls enjoy playing sports with the implied or not. So that tells me that my alternative hypothesis is going to be not equal to again. And this is going to be a 2 prop Z test. Where we have, I'm just going to let 1 be boys and 2 be girls again. So we're going to have X1 was 68 and N1 was a number, was 76. Did I get that right? This is feeling wrong. Oh, I remember that correctly. Great. And 70 out of 81 for the other one. X2 is 70 and N2 is 81. And these numbers are not particularly large. So I'm thinking that it's going to be hard to reject the null hypothesis here. Now, I should tell you, I haven't actually done this hypothesis test. I just made up the numbers and threw them into this example. So we'll see how it goes. But those proportions are looking not that different to me, and those sample sizes are looking not that large. So we're going to see how this goes, but I'm guessing we're not going to be rejecting the null hypothesis. Let's go find out. So we're going to share up a calculator. And we're going to do a stat test, 2 prop Z test. Let's get right here. And they're going to ask us for X1, N1, X2, N2. We had 68 out of 71, 76, and then 70 out of 81. 81. Did I remember all that right? It feels so bad to forget something that was like 30 seconds ago. 68 out of 76, 70 out of 81. But it's surprisingly hard to talk and think and keep things in my brain all at the same time. It doesn't work out very well. I think my brain's not equipped for that. Alternative hypothesis not equal to, let's calculate it up. P1 hat 89%, P2 hat 86%. Yeah, there's no way. P-value 0.557. Yeah, not even close to rejecting the null hypothesis here. There's not evidence that we should reject the null hypothesis. So that's what I'm going to say on the whiteboard here. P-value 0.557. P-value about equal to 55.7%. Don't reject the null hypothesis. And let's write a nice little conclusion that could be understood by even a layperson to statistics. It's all in pink for some reason. I was never writing in pink. What the heck? This is not enough evidence to suggest that boys and girls, the proportion of boys and proportion of girls who like to play sports is different, to suggest that the proportion of boys and the proportion of girls who enjoy playing sports is different. There you go. Good enough. Now, what that should say is I'm going to do the confidence interval right now. What that should mean is that the confidence interval should contain 0. So I will be surprised if it doesn't. All right, so let's do our confidence interval here. So we're going to make a 95% confidence interval. So this is going to be a 2 prop Z interval. Same data as hypothesis test. I don't particularly feel the need to write that again. All right, so we're going to go to calculator, stat, test, 2 prop z interval. Let's test 2 prop z interval right here. 68 out of 76, 70 out of 81, 95%. Looks all great to me. Calculate it up. Yep, and indeed 0 is in the interval. So we got negative 0.07, so about negative 7.1% up to positive 13.2%. We get negative 0.071 up to 0.132 is our confidence interval. So let's interpret our interval as we should. So we are 95% confident that the difference between between the proportion of boys and proportion of girls who enjoy playing sports is between negative 7.1% and plus 13.2%, with negative numbers corresponding to a higher of girls. And positive numbers, I think that's implied. Yeah, there we go. So pretty much same as before. 0 is in the interval, right? Negative 7% plus 13%. 0 is clearly between those things. And I don't have too much more to say. I think I just want to jump into paired testing because there's a bit to explain about how paired testing works and what it is. So yeah, so here we go. Okay. So paired tests are not like the other 2-sample hypothesis tests. It's not even really a 2-sample test, although we do have 2 samples and we are interested in the differences between them. It's not the difference between the means of each sample that we're interested in. It's what we do is we find individual differences. And so what that means is there has to be some sort of connection between each individual in one sample and some corresponding individual in the other sample. You have to be able to match them up 1-to-1, and you have to be interested in the difference in what you're measuring between the 2 of them. So here's what I mean by that. So some common examples are, let's see here, I have, so the most common one's probably before and after. So weight loss, or for example, which is the one I'm going to do a weight loss example here in a bit, or testing to see if some medicine works correctly, or testing to see if, you take a test and then you learn something and then you try and take the test again, see if your results have improved, right? Those are all common results for before and after. In psychology especially, and in some social science experiments, they use twins a lot because they want to take like genetic factors out of whatever they're testing. And so twins, I don't know if you guys know this, but identical twins have the same genes. And so twins are actually very sought after for medical tests and for psychological tests for this exact reason, which is kind of interesting. But there's an obvious connection there, right? We get one twin in one group, the other twin in the other group, and you do something to them and test to see like what the different outcomes give you. Sometimes it'll just be siblings. Like if you and your sister grew up in the same household, like what divergent effects did that have, kind of thing. Tests on married couples, right? So does the husband or wife make more money? Which partner in the marriage does more of the housework, et cetera, et cetera, et cetera. Right? So things where there's some specific connection between person in one sample, person in the other sample. So you have to have some sort of special 1-to-1 connection like this to do a paired t-test. So they're not they're actually pretty common, but they're not super easy to set up. They're not like a natural thing that just occurs. You have to really set it up. It's hard to get a 2-sample t-test that's not an experiment that you've set up in some way. So let's see here. So I guess the natural question then is why? Why would you spend all the time and effort to do this if it's just like you could just do a 2 independent sample t-test and not have to spend the time and effort? Well, it turns out that a paired t-test is more effective at detecting differences than a 2 independent samples t-test is. And the reason it's more effective is with the two independent samples test, here's the thing I want to see. So how can I say this? I want to show you my example that we're going to do, and then talk about why paired test in that context. In fact, maybe we'll do the test both ways, and we can talk about whether it would be detected as a difference or not. So let's do that. So here's the example. I've got it all in a file or in data file. I'm going to show you what we're going to do with it. So Dr. Henry Valora is testing a weight loss treatment. He recruits 50 overweight people to test the treatment, and the results are in this file. And we're going to do a hypothesis test and a confidence interval just like before. So let's go look at the file. I think I have that open, right? Where is it this one? It's this one, but not there. It's over here, weight loss data. Yeah. Okay, so what I've gotten here is before and after, right? So I've got the weights of 50 overweight people over here before they did the test and after they did the test. And so here's the thing I want to point out. So firstly, let me explain what we're going to do, and then I will talk about why we want to do it or why we would prefer to do this. So what we're going to do is we're going to find the differences in weight lost. The amount of weight lost is what I'm trying to say here. So I'm going to have negative numbers corresponding to weight lost and positive numbers corresponding to weight gain, because some of the people in this sample gained weight. So let me actually go back here and write some hypotheses, because this is going to be the order you do the subtraction in is really important. Why do I don't have any blank sheets? Oh my God, my whiteboard is going to be a mess. All right, so my null hypothesis is that the test doesn't work. And here I'm going to comment on what your book does, and in fact, what every book I've seen does that I absolutely despise. So I'm going to do after minus before. If you after minus before, then positive changes will show up as positive numbers and negative changes will show up as negative numbers, which is to say, if someone gains weight, the number will be positive that you get. If someone loses weight, the number you get will be negative. Similarly, if you have done take the SAT, then take an SAT prep course, and then take the SAT again, some positive change will show up as a positive number if you do after minus before. So in general, I always do after minus before. I think it makes the most sense. It works fine, like mathematically, if you do before minus after. So you can do that if you want to, but I would not recommend it because the results feel very counterintuitive to me with negative numbers corresponding to positive changes. So what I'm going to have is I'm going to have mu before minus mu after. No, I just said what I was going to do it in the other order. Gosh darn it. Spent a whole bunch of time explaining. Let's try this again, because sorry, I've done things differently in different classes before, and it's kind of running into what we're doing here. Mu after and mu before. If the weight loss program works, the average weight after will be smaller than the average weight before, right? Because the people will have lost weight. So something like this. Then the null hypothesis goes like that. So if I was doing a SAT prep course, which is one of my common questions here, I would have something like it would be mu after greater than mu before, because you would have a greater score after the prep course than before it. Here, if everything worked correctly, you will have a lower weight after the weight loss program than before it. So mu A would be less than mu B, right? Mu after would be less than mu before. Okay, so here's a really important thing to notice. I need mu A less than mu B. This corresponds to mu A minus mu B is less than 0. Now, all I just did some basic algebra. I just subtracted mu B from both sides. And the reason I care about that is that I have to do the subtraction in this order to use that alternative hypothesis. And that's what the calculator is going to ask us for, is do we want this to be, greater than, less than, or not equal to? And so the order of subtraction determines what direction the symbol in the alternative hypothesis points. So be really careful with this. I know I'm hitting this really hard. This is shockingly hard to get right. Like I'm not even kidding. This is like the hardest part of the test, or the hardest part of this hypothesis test. And I know that sounds ridiculous, but it's true. I guarantee when you're doing some of these, you'll mess them up. I certainly have in the past, more times than I can count. So the reason I care about that is that I'm about to do some subtraction over here. I want to do after minus before for each one of these. So each of these is a person, right? This person started at 308 pounds, did the program, is now 304. So they lost 4 pounds. Good for them. This person started at 293, ended up at 295. They gained 2 pounds. Boom. So what I want to do is I want to subtract each one of these. I'm going to do after, which is B, and before, which is an A, which is oddly backwards. So this is going to be equals, so I'm going to do B2 minus A2. And then I wish they wouldn't autofill. I think that's actually correct, but and I'm going to pull this down to all 50 people, and I'm going to make a point. All right, so let's go look at the results. So the difference is -4, 2, so gained 2, gained 1, lost 1, gained 4, lost 10, lost 5, stayed the same, gained 1, lost 2, lost 4, lost 5, lost 3, lost 13, etc. I'm not going to say them all out loud. So it looks like we have more losing than loss, -17, more weight lost than weight gained, which is good. Like that's an indication that the program probably works. So what I want to do is the following. I want to find the average, right? So average of A2 through A51, I think. Yeah. So the average weight before is 252.46, and I want to do the standard deviation. A2 to A51. I said 52, I meant 51. All right, and then we've got equals average of B2 to B51. All right, 31 and 51. All right, so it looks like the average weight loss was like 5-ish pounds. Now, I want to do standard deviation here. Standard deviation of B2 to B51 and make a point. So it looks like the average weight loss was it was like 4.5 pounds. That's not a tremendous amount of difference in the average. And the standard deviations are like 44 and 45 pounds. That relatively small amount of change in the average is going to be very hard to detect when the differences are this, or when the data is this inconsistent, right? A standard deviation of 44 or 45 with a difference in means of just 4 or 4.5 pounds is probably not going to be detectable if we did a 2 independent samples t-test. However, the thing I want to do here is average of C2 through C51. Yeah, so 4.5 pounds. And then I'm going to find the standard deviation of C2 through C51. The standard deviation here is just 5. That probably makes this detectable, right? The data here, if I look at these samples independently of each other, is very inconsistent. 40, 45, 44, 45 standard deviation. However, these data aren't actually independent, right? This, like, we don't really have a range of whatever 173 up to 308 or whatever, 325, whatever the max is. Because we actually don't care how much they weighed beforehand. We only, or before or after, we only care about how much weight they lost. And there's not that much of a difference there, right? The variation in the amount of weight lost is not that big, even though the variation of the amount of the weights of the people in the study is comparatively much larger. This is why we do a paired test, is because we don't have to worry about, we don't have to compare the 211-pound person and the 314-pound person. We only have to compare the negative 10 pounds lost and the negative 5 pounds lost, right? So there's a lot more of a difference in the data, in the raw data in each sample than there is in the differences. Or there's a much greater range in the raw data than there is in the differences. So that's why you want to do a paired test, is to account for the fact that the people in your study, like you don't have to worry about the starting or ending values of the people in your study, only what the differences are. And very often those differences will be relatively small compared to the change in the raw data from the participants. So that's why this is useful, or that's why it's useful to do a t-test like this. So now, remember I said that a t-test, a paired t-test, isn't even really a 2-sample test, and it's not. All I'm going to do is a 1-sample test on this column, on the differences column. I don't care about the original weights or the weights before or after. I only care how much they changed. So what I'm going to do is a 2-sample difference, or excuse me, 2-sample difference, a 1-sample hypothesis test on the differences. So the thing I care about is this and this. Now, let me mention the thing that I hate the way books do. The books that I have seen, including your book, including this one, write this, mu A minus mu B, like this. They just call it mu D, the mean of the differences, less than 0. The reason I don't like that is it's really important the order in which you subtract. Doing after minus before is different than doing before minus after. You could do before minus after, it is in red, if you wanted to do mu B minus mu A, then you would be checking to see if the result that you got was greater than 0. Because if before minus after is big, that means that the weight before was big compared to the weight after, which would be what you want if you're checking to see for weight loss, right? You'd want before to be bigger than after. Now, I understand this is super confusing, which is why I don't like doing this mu D stuff, because this doesn't tell you the order you subtracted in. And I think that's terrible. So I want to do mu A minus mu B. If you write it as mu D, I'm not going to mark you wrong. It's fine. Books do that. All the books do that. I wish they wouldn't. I feel like it makes this harder than it needs to be. But if you want to, go right ahead. You could also, like, if you wanted to have just a single thing, because it's really just a single sample, so having mu A minus mu B is a little bit confusing in the sense that that really looks like you've got 2 samples, but you're really doing a 1-sample hypothesis test. So that can be, there's a little bit of a mismatch there. If you want, you could write it something like this: mu after minus before is negative, right? That's the same thing. Then we just have the 1 mu with kind of a complicated subscript rather than the 2 different mu's. That's fine too. This is fine. This is fine. This is terrible, but I won't mark it wrong. All of those are okay. I usually do this one. The fact that it's 2 different mu's doesn't confuse me personally. it might confuse you. And if it does, then maybe try this one right here with the single mu and a minus b in the subscript to tell you what order that you're subtracting in. Right? That tells you just as well what order you're subtracting in, so that's fine with me. I think that's okay too. Anyway, let's do this test. Now, I'm going to go to the calculator. Actually, I'm not going to go to the calculator. I'm going to go to the weight loss data because I need to know these numbers, right? We have an N of 50. And notice it's just 50. It's not 100. We don't really have two different samples of size 50. What we have is one sample of differences, and there's 50 differences. So I've got N of 50. The mean difference is negative 4.5, and the standard deviation was 5.33. Now I can go to the calculator. And when we go to the calculator, you're going to notice that there is no paired t-test because this is just a plain old one sample t-test. We're going to put in the stats. mu0 is 0 because we are looking at these hypotheses, which this is where the 0, this is where writing them like this is really helpful. I'm gonna give myself a line. Boy, I've really made a mess of this thing, haven't I? This is gonna be some nice whiteboard for you to try and sort through. So I'm thinking of this as not HA. That's not what I'm trying to say. U sub A. Let's see, after minus before greater than or equal to 0, and then mu after minus before less than 0. Right, that's really what I'm going to try to do. This is just god awful. I have to redo that. I'm sorry. I can't live with the way that looks. Okay, so we're going to have mu sub after minus before greater than or equal to 0, mu after minus before less than 0. All right, that's at least readable. I can live with this. That's what we're testing. And so we have our X bar after minus before is our sample mean. All right, let's go over here. I'll annotate this up. Good pink. So we've got this guy right here is X bar after minus before stat. Then we have this is our S after minus before, which your book will call S sub D for difference again. And then N A minus B is 50. Okay, so negative 4.5, 5.33, and 50. Let's go to a t-test. So mu0 is 0. X bar was negative. Oh, that's right. Sorry, negative 4.5. I also got a syntax error there. 5.33, and N was 50. And I think we might be able to reject the null hypothesis here, mid less than. Yeah, look at that tiny p-value, d of negative 6. All right, so we've got 1.3 times 10 to the negative 7 p-value. I don't need to carry a lot of decimal accuracy. I'm just comparing it to 5%. So, obviously less than 5%, even if I don't round off super accurately. Where was I at? That one. All right, so conduct a hypothesis test. We did that after a fair bit of explaining. Let's get another page here. Got more A continued, get a t-test with X bar was negative 4.5. S was 5.33, and then N was 50, and we got p-value approximately equal to 0.12345613, which is clearly less than 5%. Oh, no, computer, go away. I didn't mean to touch the side of my screen. I'm sorry. There we go. So reject null hypothesis. Woohoo. All right, so rejecting the null hypothesis means that we think that the average weight after is smaller than the average weight before, right? Mu A is less than mu B. So mu after is less than mu before, which is another way of saying we think the diet works, which is great. So let's write a conclusion with the text function. According to this data, the diet seems to work. Great success. I don't think we need, I don't think I need any more than that. So this is the sort of plain English conclusion that anybody could understand. So fantastic, I'm happy with that. And it gets across the red idea. So I hope that was clear enough what we did with the t-test, what we did with the paired t-test, and why a paired t-test, even though we have two samples, is really a one sample test. We do have two samples, but the only thing that we're interested in is the sample of differences. So we just do a one sample test on the differences, almost always comparing to zero, right? Almost always. All right, and we want to make a confidence interval. So confidence interval is going to use exactly the same data. We're going to make a 95% confidence interval. We're going to use x bar negative 4.5, s 5.33, and n 50. So let's make a page for that. So B, whoop, that's not the right thing. T interval. So this is the same data. Same beta? No, that's not how that works. That's not how words work. Same data as the test. And let's just go jam it into the calculator and see what we get. So we're going to go to the t interval, stat tests, t interval number 8. And the stats are already in there for us. I like how the calculator tries to pre-guess what we're doing here. So fantastic. That is in fact what we want. Confidence level 95% sounds good to me. Calculate. All right, so we got negative 6.015 to negative 2.985, which is good. Negative numbers correspond to weight loss, so that's fantastic. Yeah, negative 6.015, negative 2.895. Best we get negative 6.015 to negative 2.985. So let's write a conclusion. See, nice little text function. We are 95% confident of something. That the average weight loss using this treatment and is between 2.985 pounds and 6.015, not 60, 6.015 pounds. Yeah, there we go. Hope that's clear enough. I think that's all I want to say there. So let me briefly sum up and then end this long video, and I'll see if I can rearrange the pages. It's all one PDF file, but I don't know if the pages are movable. All right, summing up. Do two sample hypothesis test if you got two samples that are being compared to each other. And they have to be compared to each other, not like separately to a number, right? Two samples that are being compared to each other, that's what the two sample hypothesis tests are for. There's 3 of them. There is two sample t-test, two prop z-test, and a paired t-test. There is technically a two sample z-test. I will not ask you to do one. I think they're pretty pointless. Yeah, so two sample, this two sample t, I kind of want to call this, oops, that's not how we do that. I kind of want to call this that independent, two independent sample t, and paired is dependent samples, two dependent sample paired t, something like that. But I'm going to keep them the same name as your calculator uses, just so it's easier to remember which one to do. So yeah, 2 sample t-test is for 2 independent numerical samples. 2 proportion z-test is for 2, oh my gosh, I hate when it does this, it leaves my name on there. 2 independent, or excuse me, yeah, 2 independent proportions. Why are we doing this? There we go. Good enough. 2 independent proportions. There's no dependent proportions one. And then paired is when you have that specific matching up that you can do from one sample to the other. And it has to be like really specific, before and after being by far the most common, where you're matching up somebody with themselves, like we did in the weight loss example. And then after that, same process as before. Read through the problem once to get a good idea of it, of what's in it. Read through it again very carefully, labeling all the numbers. And then from here on out, pretty much just jam it in your calculator. Not that interested in all the other steps of the test, because we're not going to do very many hand calculations, if any. We're not going to do much normal CDF or anything like that. Pretty much going to leave it to the calculator to do the test and produce the p-value. It's just a lot shorter that way. And I think that's the way the world is going anyway. So I'm not going to worry about writing out absolutely everything. I want you to get familiar with using the calculator. And when you do, please tell me what you put in. Something like this is very informative to me, because then I can tell what you've done and whether what you've done makes any sense or not, and if your interpretation makes sense. So show me what you've done there. 2 proportions is for when you have categorical data. You have 2 samples of categorical data that you were comparing to each other. And then paired is when you have 2 dependent samples where you can match up one person in one sample with one person in the other sample. You can match them up 1-to-1. Normally you can't do that, right? This is a thing that you have to set up. You can't, like, paired t-tests don't just like show up in the wild, right? You don't just get 40 pairs of twins walking around, then you can do a medical treatment on one and not on the other one and see what happens, right? That's not how that works. You got to set that thing up. So yeah, those are the kinds of tests that we're going to do. We're going to use the calculators. You still do have to write hypotheses. Writing the hypotheses and interpreting the results is more important now than ever, because the numbers that you're going to get, it's a little easier to lose track of where they're coming from, because you're just kind of jamming them all on a calculator, right? And then hopefully the number that you get means something and is the right thing. And right, there's no like visual aids of a distribution kind of guiding you along to what you do next. It's nothing like that. It's just you read carefully, put it in the calculator, get the results, interpret the results correctly, and you're good to go. So writing hypotheses is super important. And with that in mind, I think I want to go ahead and call that a video and go see if I can fix the whiteboard. All right. Thank you guys for watching. I will see you guys in the next video.